and the next video we will look at a lock-free stack implementation. And we will use an atomic top variable and next pointers and not an array. Okay, because using next pointers makes this more, well, it has both advantages and disadvantages, which are the same for single-threaded programs. I mean, an array is more efficient, but that is not what we are concerned with now. Now we want to get problems due to lock-free data structures. Okay, I mean, we want to learn about them. So let's do this as follows. We have top variable initially pointing to a null pointer, and then some node wants to push something. Okay, so we can say that a node pushes 2 on this stack. What should happen? I mean, everyone knows this, but I will draw this figure anyway. Okay, so now the top of the stack is pointing to, I mean, the variable points to this one, and say we want to push something more, then it should point to the current value, and the top should be there, etc. Okay, so how should we do this with a multi-threaded program without the lock? What I said that the top variable should be atomic, and that's quite clear, since multiple threads may want to modify this. They want to modify it at the same time, possibly. Of course, only one of them will succeed in modifying it, but it must be atomic, since it's not protected by a lock, and several may want to modify it and access it at the same time. Okay, so that's clear that this one should be atomic, but these next pointers, should they also be atomic? They should be atomic if multiple threads may want to access it at the same time, and at least one of them does a write. But that is not needed for a stack, since the only pointers that are modified that can be modified by multiple threads is really only the top of the stack. Once a node is here, no one will change it concurrently with anyone else. Okay, so what should a thread... I just draw this picture to see what we are doing, but what should a thread do when it wants to insert or push an item? There are 3 stores involved, and the question is in which order we should do them. So it starts with creating a new node. Oh well, it's better if we use this color. So we create a new store, a new node. So the first store is to write the 7 there. And then the question is, should we modify the top pointer to point there first, or should we? No, of course we should not. Partly because we lose the pointer to number 5, but that's a very serious problem if we would do that. But what is also a serious problem is that if we would link an incomplete node into the stack so that anyone else would be able to see it, then we would have a corrupt stack. So that's not a good thing to do. We can set the pointer to that, and now we can try to set the top to this node. But let's say now that another thread is also interested in doing that. So here comes another thread, and it will try to push 11, and actually a third thread will try to push 13. Okay, so they all do that and that, and then they will use the atomic compare exchange function. And what will they do? What should they use as parameters? They should do as follows. Well, should I draw this? Well, I can do that, but I will abbreviate the name compare exchange. Okay, so now we give the address of the atomic variable, and we give the address of the variable that has the value that we hope is equal to the top. Okay, and which one is that? Okay, so a node here, it contains two things. It contains a key and it contains the next. That's a node. So if we each thread here must have a local variable that points to this, to the node that the thread just created, so we can call it A. So this one is for thread 3, so we can call that A3 and A1 and A2. But it's a local variable A. Okay, so what should we have here? We should have the address of this field. So it's this one. When this function checks the first two parameters, it gets pointers to these variables, and it will use the pointer to get the value. Okay, and then what is the new value that we want to set to top? Top should be the new value if these two are equal. Not the parameters, but what they point to. So here it should simply be A. Okay, so let's see what should happen. If they are, what they point to are equal, then the top variable will point to the third argument, or get the value of the third argument. So what would happen then if, one of these will succeed, and say it's thread 3. So it will do the following. It will move the top to this one. Okay? So that thread is happy. And what will the others do? They will also do this atomic compare exchange. And they have, when they do that, they take the current value of the top, since they supply the address of the top, so this function can evaluate the current value, and then they supply the next of their newly created node, which of course is a node with a 5, and that's not the top, since the top points to 13. So this one will fail. And what is nice with this function is that if it fails due to these are not equal, then the current value of top will be copied into this variable. Okay, And that's exactly what we want actually. So let's say we can look at thread 1 because it's closer to this one. Okay, so when it calls this, the function checks top and the next of this, and they are not the same. So it changes this one to point to the top. Okay, and well, the same thing will of course happen for this when it goes there. And well, okay, this will be increasingly dramatic figure with lots of arrows. Not dramatic, but well, something. Okay, and now both of these will try to do atomic compare exchange again, and one of them will succeed and the other will not. And the third, I mean the one which will not, will get its the next field of the object updated, and eventually it will succeed. Okay, the API is actually not called this because it has either weak or strong here. Or strong. Okay, and as I have mentioned previously in the course, weak may fail due to other reasons than they were not equal. And in architectures such as Power or ARM, it can fail due to load linked and store conditional didn't work because some other thread has modified the data in between, or on Power it's called load and reserve. And in that case, it's not copied. Okay, and this weak, it should be used when we have this in a loop, because, well, there's no point in using this, since we will, if it fails, we will just loop to the next, I mean, continue until it succeeds. And the strong, it's more expensive on some architectures, such as the ones I mentioned, but it's guaranteed to succeed. Okay, and it's not needed if we have a loop anyway. Okay, so it's better to use weak when we have a loop and strong when it's not a loop. And when we really require that it should succeed. Sometimes we don't care because some other thread may do the work for us anyway, or the work has already been completed, so we shouldn't do it again. We will see an example of that in when we look at the queue in another video today. Okay, so let's look at the source code. Here is we can look at the types. The node is just as it would be in single-threaded program, and the stack has an atomic pointer, and we initialize the stack by setting everything to zeros, and then we push by setting first creating a new node and then setting the next to the current value of the stack, the stack pointer, and then we loop until we succeed. Okay, so that's the push.